Okay. Good afternoon, everyone. I'm Wang Hui from Chongqing University of Technology. It's my pleasure to present our work on the parameter-efficient adaptation of Weixin foundation models for multitask ultrasound imaging analysis framework we call type SLF. In clinical ultrasound diagnosis, experts often perform segmentation, classification, and detection simultaneously. While foundation models are powerful, for fine-tuning on limited medical datasets is computationally expensive and risks destroying trained representations. Our goal is to develop a unified framework that preserves the generic knowledge while enabling lightweight task-aware adaptation. Here is our type SLF architecture built upon a shared Florence Joule encoder. We implement a selective strategy. The bottom 70% of layers are frozen to maintain stability, while the top 30% are adapted via NORA. We also inject task-aware soft props for segmentation, classification, and regression to guide the model, while allowing the detection paths to bypass the prompting to preserve spatial alignment. To validate our approach, we utilized the FMCUIA 2026 challenge dataset. Our evaluation covers the comprehensive suite of metrics from DSC and HT95 for segmentation to MIOU for detection and MRE for regression. We compared the type SF against the official baseline and popular methods like standard NORA and VPT. To get the quantitative results in type 2, type SLF consistently outperforms other methods across the key metrics, particularly in segmentation with a DSC of 0.942723 compared to standard NORA. Our framework achieves higher precision with fair trainable parameters, demonstrating the effectiveness of our task-aware approach. To further understand the contribution of each component, we conducted validation studies. The results in Table 3 confirm that both the task-aware property and selective layer fine-tuning are essential. Their combination yields the best multitask synergy and effectively mitigates active transfer between tasks. We also investigated the impact of different frozen ratios, as shown in Table 4. Freezing 70% of the layers provides the best balance. Over-freezing leads to underfitting, while excessive fine-tuning causes overfitting. Proving that precise control of parameter updates is key in specialized medical domains. Yes, this slide shows our segmentation results on lateral cervical images. Comparing our predictions with the ground truth, you can see that type of SLF accurately delimits the anterior and posterior lips. The clear boundaries demonstrate the model's strong spatial discrimination even in noisy ultrasound backgrounds. To conclude, the typical SLF offers efficient and flexible paradigm for adapting foundation models. Currently, we rank fifth in the overall challenge standings. Our implementation is available on GitHub, and we hope this framework inspires further research in multi-task medical imaging analysis. Thank you for your attention.
Thank you for your for sharing your solutions. There is much time for discussions. Is there any question? Is there any question to Hui Wan? Eric can if you have, you can ask him directly.
Hello. I want to ask about the training of your model. Just you said that you fine-tune VRM by lower. How much GPU did you use, and can you share the training time about your experiment?
GPU is 3019 and
1319 GPU.
yeah, and
the training time about your experiment.
about 2 days experience. And the video memory is about 5G.
5T that's parameters one. 5TB. The model is so big.
About your model size.
Training a model takes up 5 GB of GPU memory.
Oh.
5 GPU. What's your GPU card? A100 or other GPU? The version of your GPU card, can you share about this? How many GB is each one of your GPU? Is
24 or 48 about your GPU memory.
The GPU memory is 24 GB.
Okay.
24 times you have 5 GPU. That's a lot of GPU.
Yeah, it's
Okay.
It's about 24 times 5, totally 120 GB. Oh, thank you.
Is there any question?
I ask a question. What is the backbone model? Thank you.
About your backbone.
对，backbone yeah.
Florence too.
Okay, thank you.
Okay. Other question? If not, we will investigate the Dr. Ma give the solutions for this challenge.
Okay, thank you, Professor Bai. I will share my slide. Good afternoon, everyone. I'm very pleased to present our work, Unified Ultrasound Intelligence toward an end-to-end agentic system. Ultrasound is widely used, but it is highly variable. In real clinical settings, image appearance can change a lot because of spectral noise, different operators, different devices, and different acquisition protocols. Because of this variability, single-task ultrasound models often generalize poorly, especially when they are applied across datasets or clinical scenarios. So what we need is not only more transferable feature learning, but also a framework that can better support end-to-end clinical workflows. At the same time, there are several important challenges. First is multitasking heterogeneity. In our setting, we need to handle 4 task types and 27 subtasks, including segmentation, classification, detection, and regression, which require very different output spaces. The second is negative transfer. When different tasks share one backbone, the model must balance competing objectives. A shared representation can be useful, but it can also create interference across tasks. Third, there is a workflow gap. In real clinical practice, ultrasound analysis is often a multi-step process rather than an isolated single prediction. So the goal of this work is to build unified ultrasound intelligence from multitask learning to agentic workflows. This slide shows the overall design of our framework, which we call US tree, meaning tree-stage ultrasound intelligence. The framework contains 3 stages. In stage 1, the universal generalist US gene learns broad and transferable ultrasound representations from heterogeneous data. In stage 2, the lightweight specialist USPEC adapts the general backbone to specific downstream datasets and tasks in a parameter-efficient way to get best performance in the competition. In stage 3, the specialized models are organized as callable tools and used for end-to-end agentic system US agent. So the logic of the framework is very clear. First, learn general knowledge, then specialize efficiently, and finally integrate those specialists into an end-to-end agentic system. Now I will explain the first stage in more detail. In USGen, we train a universal backbone on heterogeneous ultrasound images. On top of this shared backbone, we attach task-specific head for the 4 task types. And the key idea here is the dataset rotation detail, a rotation schedule. Instead of optimizing all datasets at the same time in a fully mixed way, we optimize one dataset at a time and then cycle through all datasets, which helps the model learn from diverse ultrasound domains while reducing direct cross-task interference. So stage 1 builds a strong and transferable general foundation for ultrasound intelligence. After obtaining the general backbone, we move to stage 2 USPEC. Here we freeze the stage 1 backbone, then instead of retraining a full model for each downstream task, we fine-tune only 27 compact dataset-specific heads. It is parameter efficient and it improves per dataset task and level alignment, which is especially useful under changes in view device or annotation style. So USBAC keeps the benefit of a shared general backbone, but adds the flexibility needed for real downstream robustness and gets the best performance. After presenting the change-oriented modeling stage, we move to US Agent, which is our beyond change extension. US Agent is a biomedical viral language model-based agent designed for comprehensive end-to-end ultrasound analysis. Its core idea is to treat the trained USBAC specialist as callable tools. A planner receives the query, decides which task is needed, routes it to the appropriate specialist, executes the tool, and stores intermediate results in a state cache, and then produces the final output. This is important because real clinical analysis is often not a single-step process. A system may first need to localize a region, then segment it, and then perform regression or classification, and finally generate a structured output. US Agent supports exactly this type of interpretable multi-step reasoning. It preserves intermediate evidence, such as regions of interest and task output, and then generates a more structured clinical result. This slide summarizes the implementation details. On the loss side, we use task-specific objectives. We use dice loss, cross-entropy loss, heat map regression with MAC loss, and box regression with an IOU-based loss for segmentation, classification, regression, and detection. And we apply equal weighting across tasks. And for test time adaptation, we use several geometry and color strategies. For geometry, we use identity, horizontal flip, and vertical flip for segmentation, regression, detection, while classification additionally uses rotations of plus and minus 30 degrees. For color variation, we use gamma and contrast adjustment for segmentation, regression, and detection, and random brightness contrast and Gaussian noise for classification. These choices improve robustness against strong appearance variability that is common in ultrasound data. And this slide introduces the dataset and pre-processing setup. Across the benchmark, we have 4 task types, and the output formats are also different. Segmentation produces image outputs, while classification, detection, and regression produce JSON-style outputs. For pre-processing, all images are resized to 256 and normalized with ImageNet normalization. For regression tasks, we generate Gaussian heat maps with sigma equal to 4 pixels. For augmentation, we use both geometric and color transformations. Now let us look at the main qualitative results. On the FMC UIA validation set, USBAC achieves the best overall performance across all 4 task types on the unseen domain validation setting. Compared with USFM, the ultrasound foundation model, USBAC further improves the key metrics, including DICE, IOU, and MRE. Compared with USGene, the gains are also consistent across every metric. This result clearly validates the benefit of stage 2 lightweight specialization. In other words, the universal backbone is strong, but the additional dataset specific adaptation is crucial for achieving the best downstream performance. After showing the quantitative benchmark of the challenge, this slide shows 2 case studies of US Agent, which represents our beyond challenge extension. In the intrapattern ultrasound case, a system first localizes the relevant anatomy and then segments the structure of interest, and finally produces a quantitative measurement such as the angle progression. In the superficial ultrasound layering case, the system identifies the layering region, refines it with segmentation, and then predicts malignancy. US agent brings specialist level perception and reasoning into a single end-to-end framework for ultrasound analysis. By chaining transparent intermediate steps, it produces clinically meaningful outputs that are both reliable and verifiable. To conclude, this work presents US-3, a unified three-stage framework for ultrasound intelligence. USGen serves as a powerful foundation model for general ultrasound understanding. USPEC provides an efficient fine-tuning paradigm for downstream task specialization, and US Agent extends the framework towards interpretable end-to-end clinical workflows. In terms of future directions, there are two main points. First, we want to generalize to more real-world ultrasound scenarios. Second, we want to explore stronger multimodal planning and longer horizon tool use so that ultrasound analysis can become more autonomous and more clinically useful. Thank you very much for your listening.
Thank you for your sharing your excellent work. Is there any question about the solutions?
Hello, I have a question. In your training of your model, it seems that there are three stages of your training. In the first stage, you trained a universal foundation model with the backbone of transit, yes. And in the second stage, you frozen the backbone is frozen and data set specific has are fine-tuned. Yes. What do you think of this pipeline? And did the CG1 and CG2, did you use the same data set?
Yes, I use the same data set. The reason I use this paradigm is because that in the stage 1, I only use 4 heads. For segmentation, detection, classification, and regression, we only use 1 head. So I think using this way, in this way, the shared backbone will be more stronger. And in the stage 2, we use 1 head for each data set. So there are 27 heads. And we frozen the USGen and only fine-tune the dataset head.
If we finish the 2 stages in just 1 stage, do you think the performance will be very low?
So stage 1's performance is shown in the table. As you can see, the USGen is lower than USPEC.
Oh, that's interesting. Thank you.
Thank you.
Do you have any question other participants? If not, I have one question about your backbone. Can you give more details about the backbone US gen? That is different from US FM model.
Yes, it is different from USFM. Because USFM is a original VIT base structure, and USGen we use the trans-unit backbone. In the trans-unit, the encoder is ResNet with VITB, so it can be more powerful. And we find that the supervised supervised USPEC is more powerful than USFM. I think it is because that they directly learn the representation required for the downstream tasks.
Okay, thank you.
Okay, thank you.
Do you have any question from other participants? If not, thank you again for your presentation. We will next invited another team give presentations. We invited the brain team do the solutions.
Yeah, can you see my screen? Hello, Professor.
Yes.
Okay. Hello, everyone. On the behalf of Brain Team, I'm Ufa Khan, and today I'm presenting our work, Aurora, that is Adaptive Unified Representation for Robust Ultrasound Analysis. So our main idea is very simple. Instead of building a separate model for every ultrasound task, we ask whether one unified model can solve multiple tasks together, especially for segmentation, detection, classification, and regression, while remaining robust across diverse ultrasound settings. So let's look at the why unified ultrasound AI. So ultrasound is one of the most widely used imaging modalities in clinical practice, but it is also one of the most variable. Like in this challenge, we deal with 27 distinct subtasks across 4 task families using a dataset of more than 6,700 training samples. So the first major issue is the domain shift. Ultrasound image varies a lot across scanners, operators, acquisition protocols, and also patient poses. So as a result, a model that performs well in one hospital may lack in another one. So the second issue is the task fragmentation. So most existing approaches train a separate model for each task, but in real clinical deployment, that is inefficient and hard to maintain. What is really need? A single robust model that can handle multiple imaging objectives together. So our work built on recent evolution of foundation models. We started from the general trend initiated by SAM, then medical adaptation with MedSAM, followed by ultrasound specific efforts such as UltraSAM and privacy aware approaches like UltraFed FM. So why this matters, it's a unified 4-task framework for ultrasound. So there are 3 main contributions. First, we use a single Quinn VL backbone to address all 4 clinical imaging tasks through a shared representation with task routing. Second, we introduce a token to map bridge, which converts transformer tokens into multi-scale spatial feature map. So this is important because transformer tokens are very powerful semantically, but dense tasks like segmentation and detection need special structure. Third, we propose an efficient joint training strategy using temperature-based task sampling and dynamic loss reweighting, so that one task does not dominate the other during training. So this is just an overview of our architecture. So the image is processed by shared Quinn encoder, which serves as a common backbone for all the tasks. Then the encoder produces the rich transformer features, and these features are token based. So to make them useful for both dense and global prediction, we pass them through our token to map bridge that implemented within layer by layer F2 to P2 to P5. This gives us a hierarchy of feature maps ranging from fine detail to high level semantic context. Then we use the task router. We directed the shared features to one of the 4 lightweight heads, that is for segmentation, detection, classification, or regression. So one encoder and one shared representation and task specific heads for different outputs. So this lets us the benefit from transfer across task without completely mixing their objectives. So this is just an overview how it works. For example, you have the ultrasound image, you will pass it to the Quinn 3VL encoder, then we have token to map, then we have the task router, which have for segmentation, they will give us the mask, for detection, they will give us the bounding box, for classification, they give us the class, and for regression, the key points. So this is our main architecture figure. So the important thing is to note is the balance between the sharing and specialization. So at the shared level, the model learns universal ultrasound features from Quinn 3VL encoder, and at the bridge level, FPN converts those token features into multi-scale maps. At the task level, each prediction head only receives the feature that it needs. So this design gives us 3 advantages. The first one is shared representation learning, which helps the transfer knowledge across anatomical targets and task types. Second is the dense plus global reasoning, because the feature pyramid supports both pixel level and image level tasks. Third one is reduced interference, like because the task router and lightweight heads limit the negative transfer. So this slide captures the central design philosophy of our method. So here is the details, like for segmentation, we use a full pyramid for P2 to P5 with like top layer decoder with gated skip connections. So the loss combines the cross entropy with soft dice loss, which helps both class discrimination and overlap quality. For detection also, we used anchor free grid on P2 and contextual information so that the head predicts the bounding box coordinates and the objectiveness. And also for classification, we apply the global average pooling across levels followed by the projection normalization. Also for regression, we again use the pooled global embeddings followed by sigmoid output to predict the normalized landmark values. So the regression log combines the smooth L1 for stable and precise landmark prediction. So while the backbone is shared, each output head is explicitly adapted to the geometry and the matrix of its task. So the main challenge in unified training is balancing heterogeneous tasks. So we address this in two ways. First, we use the temperature-based sampler. This smooths the task sampling distribution, so rarer or harder tasks receive appropriate attention during training. So to track this task difficulty over time, we maintain an exposure average loss with beta equal to 0.98. And second, we use the dynamic loss reweighting. So that clamps the weights between the two, and this prevents any single task from dominating the optimization. So the overall training setup uses the Quinn VL, which I already mentioned, with a base learning and input resolution. So the training strategy is not just a detail, it is what the unified framework is stable. So as you can see here, this summarizes like the evaluated 12 segmentation subtasks, 9 classification, and 3 detection or regression also. So the main takeaway is that the unified model remains competitive across all 4 different types despite using one shared backbone. So for segmentation, the full FPN gated skip connections gives us the strong dense predictions. For classification, the gated MLP or we can say logit making the support competitive image level recognition. For detection, the anchor-free design with contextual feature injection improves recall and bounding box precision. For regression as well, like normalized output helps us to stabilize the landmark prediction and reduce mean radical error. So rather than over-optimizing one task, Aurora achieves strong balanced performance across the full challenge scope. So this table shows us the raw specific matrix. Like I want to read every number. As you can see, the unified framework is able to produce a valid and competitive outputs across tasks with different matrix. And also here is the supports the claim that the single architecture can generalize across diverse ultrasound objectives. So to better understand like why the model works, and we perform some ablations as well. So as you can see here, this shows us the contribution of like each architecture component. So we compare progressive versions of the model using both Quinn 2.5 VL and Quinn 3 VL. So we start from the baseline, then add the FPN and then token pyramid, and then task specific heads, and finally full our architecture design. So the most important result is that like token to map bridge that provides the largest gain. So this confirms our hypothesis that transformer token alone are not sufficient for dense medical vision tasks. They need to project into structured special feature maps. We can also see like Quinn 3 VL consistently outperforms well as compared to Quinn 2.5 VL, suggesting that stronger pre-training transfer effectively into the ultrasound. Finally, the addition of the task-specific lightweight heads gives us another clear boost, showing that the complete parameter sharing is not enough. Some specialization is also necessary. So as you can see, the main insight from this ablation is like performance improves step by step as we move from plain vision language backbone to the full unified architecture. So among all the components, the token pyramid plus FPN module contributes the most because it bridges the gap between the transformer style representation and dense special prediction. and across all the configuration which supports our backbone child. So overall, the ablation validates both the architecture and the design rationale. So in conclusion, our architecture has three main contributions. First, it is like unified ultrasound foundational model and settings that handle segmentation, detection, classification, and regression. Second, the proposed token to map bridge that enables a vision language backbone to support dense prediction task by generating a multi-scale spatial pyramid. Third, our joint optimization strategy that combines temperature-based sampling and dynamic loss balancing that prevents task collapse and enables stable multitask learning across 27 subtasks. So at the same time, there are important limitations, like because the backbone is shared, negative transfer can still happen when task diverse are there. So the fixed resolution may limit the sensitivity to very small object, and resizing may reduce the geometry fidelity, which matters especially for precise landmark regression. So for future work, we are interested in like task adaptive gating, 3D ultrasound extension, or we can say multi-center federated validation and prompt conditional task switching. So overall, we believe like this architecture is like strong step towards more general and clinically deployable ultrasound AI. So that's all from my side. Thank you so much.
Thank you. How to spell your name?
It's Ufuk.
Ufuk, yeah?
Yeah.
Thank you, Ufuk. This is a solid presentation. This presentation included all the detail about this challenge. Thank you again.
Thank you so much.
Do you have any question from other participants?
Hey, hello.
Hi.
You did lots of work in your study, and very impressive.
Thank
And
you.
in your table 2, the figure shows that you use the efficient net and chain 2 and chain 3. How do you use the efficient net and the VM chain together?
Like how to I don't understand your point, like how to use like
Is the baseline of your model is efficient net or chain? What's your baseline model?
The backbone
Yes.
is chain 3, Qwin 3.
Actually table 2 is not like efficient at baseline, because table 2 only lists like the training and inference hyperparameters. So this shows us the actual backbone is Queen 3 VL, not the efficient net.
Okay.
Any questions? If not, I have one question. At the beginning, you introduced many vision foundational models like segment anything or medical segment anything models. I want to know the motivation of the use of large language models like Qwin3 in your work. Why you do not use other vision large foundational models in your study?
Okay. So because the paper is motivating the problem by showing the field from shift task specific ultrasound models. So I mentioned like MedSam, Ultrasam and UltraFed FM to explain the background, like why unified model is needed. Then existing the ultrasound foundation models still have the single task which gaps their method and tries to solve. So that's why like we tried different methods, and finally we come up with the Queen 3VL.
Okay. Thank you. Do you have any questions from other participants? If not, thank you again for your impressive presentation and the solid work. Thank you again.
Thank you so much. Thank you.
Next, we will invite another team, Lab 105, give their solutions for this challenge. Hello. Is there any members from the Lab 105 team? Maybe they do not come here now. Okay. If so, we will invite another team. Flamengo. Give their
Sorry,
solutions.
sorry. Where's Ultra TAR?
Oh,
where-
sorry. Sorry for that. The next team is Ultra TAR. Give their solutions.
okay, waiting.
Okay. Thank you. Thank you for your remind me. I miss your great team. Sorry for that.
Good afternoon, everyone. My name is Yishen Zhang, and I'm here on behalf of our team from the University of Nottingham, Ningbo, China, and the Hong Kong Polytechnic University. Today, I will present our solution for the ISBI 2026 foundation model change for ultrasound image analysis. Our framework is called UltraTAR, a parameter efficient foundation model with task-aware routing for heterogeneous multi-task learning. The challenge asks to build a single generalized model for ultrasound image analysis covering classification, segmentation, detection, and regression across diverse organs and pathologies. The benchmark is large scale and multi-center with tens of thousands of images showing high heterogeneity in image quality, anatomical views, and acquisition devices. In total, there are 27 subtasks, 9 classification, 12 segmentation, 3 regression, and 3 detection. So why is the changing? Most existing ultrasound AI models are narrow, designed for one anatomy or one task. The field is moving toward generalist medical AI, where a unified architecture handles device objectives, but namely training one model on or 27 tasks introduces various problems. First, the negative transfer. These tasks like segmentation and global tasks like classification can hurt each other when jointly optimized. Second, architectural mismatch, where the produces single-scale features, while dense tasks need multi-scale representations. So the optimization conflicts. 27 tasks with conflicting gradings lead to poor convergence without careful design. So our goal is threefold. Build a universal ultrasound foundation model that works across anatomical boundaries. Adapt its parameter efficiently without fault retraining, and harmonize multitask optimization to mitigate the interference between heterogeneous tasks. So it's here our architecture and it's a paper. Okay, here is an overview of Ultra tier 3K design choices. For the PFT-based adaptation, we keep the Dino-V3 variety large backbone frozen and inject LoRa depths into the attention and the MLP layers. This preserves pre-trained representations while efficiently lowering ultrasound-specific features. Second, task-aware dual branch routing. The idea of separating dense and global pathways is well established in multitask learning literature. In our case, we found this separation essential for this change. Dense task goes through a feature pyramids adapter that constructs multi-scale features from the variety outputs. Global tasks go through a CLS-guided fusion module that combines the CLS token with puts special features. This prevents the two task familiars from interfering with each other. Third, empirical loss scaling and anchor-free synchronized had to stabilize joint optimization across the 27 subtasks. Let me walk through the architecture in more detail. The backbone is a frozen Dino-V3 very large with 24 transformer blocks. LoRa with rank 64 is injected into the QKV projection output and both MLP layers. So both attention and feed-forward pathways are adapted. For the dense branch, the feature pyramid adapter takes the 24 multiple 24 patch token output and builds a 4-level feature pyramid and slides 4, 8, 16, and 32 using transpose convolutions for upsampling and spread convolutions for downsampling. Each followed by batch normalization and Giroux. This feed into a standard FPN decoder. Segmentation use a multiple one convolution heads with 4 multiple bilinear upsampling. Detection use an anchor-free synchronized heads with 2 branches, Headman branch for synchronized localization and a with haste branch for bounding box regression. For a global branch, we concatenate the sales token with global average pulled features and feed these into dedicated classification and regression tests. For the experimental setup, the dataset and the evolution metrics are shown on this slide. Each task category use is standard metrics or standards by change platform. As you can see from this table, our model achieves substantial improvements over the official baseline across every metrics. For the ablation study, we validated our design model stage-by-stage manner. Configuration A is Dino V3, small with full functioning and no architectural adaptation. In B, we switch to a frozen Dino V3 base with LoRa and add the feature pyramid adapter, solenoid heads, and empirical loss scaling. In C, we scale up to Dino V3 large and add CALS guided feature fusion, completing the dual branch routing. And D, as test time augmentation for segmentation. As the table shown, each stage brings consistent improvements, validating our design choices. Here's final ranking results. Where we didn't rank first on any individual task, we achieved the first place overall in the multi-task ranking. It's worth noting that we ranked the second on the classification task, which we largely attribute to the sales guided fusion strategy. These are randomly sampled visualizations from the validation sets across all 4 task types: fetal femur length regression, fetal plane classification, and fetal abdomen segmentation, and thyroid nodule detection. The performance looks strong across the board. In summary, Ultra TAR adapts a frozen Dino V3 backbone with LoRa and a task-aware dual branch routing strategy to handle 27 heterogeneous ultrasound tasks in a unified framework. The feature pyramid adapter and the sales-guided future fusion bridge single-scale variety features to diverse task requirements. And the code is available and the link show and is not public. That's all for my presentation. Thank you for listening.
Thank you again. I'm apologize for miss your guys. Next we will indicate as the participated. If they have any question, they can ask Dr. Zhang directly. Is there any question?
Hello. Why the Fightini is not better than the LoRa? Because I think the Fightini in the LLM is the better than LoRa, but you experiment the LoRa is the better. Do you know? Because my English is poor. Do you know what I say?
You say we don't use you say we use LoRa?
Yeah, because I train the LLM large language model. The full Fightini is better than the LoRa. But you is experiment is not the better. It's upper size.
We use the LoRa to adapt the variety, meaning use less parameters to achieve the alternative performance. We use the in the experiment process we use a single GPU A5000 RTX A5000 and it is the 24 GB. So we use LoRa, not for Fontaining.
Because the GPU is not enough, right?
Yeah, yes.
Okay. Thank you.
Is there any questions?
Hello, I have a question. Just you said that in your network you use the Dino V3 as the backbone of your network. Did you try any other backbones like CNN, for example, Copynext, or other vision transformer backbones? Because in my experiments, I found that Dino V2 is even better than Dino V3. It's very interesting. Do you have any idea about the choice of the backbone?
Yeah, I think it's interesting. You said the common next. Actually, in the experiment process, we use the common next variety as my model's backbone. But I think it's not better on validation results. So we alter to the Dino V3.
Dino V3 is really a better backbone. I'm trying to use it. Thank you.
I think there is another factor is about the associated with your good performance. I say the input size you used is 500 5 plus 500 12. Most of the other teams use a small size. I think this is a key factors associated your better performance. What about how about your comments about this factor?
Yeah, you said it's good. I think it's a part of the good performance. And then our team, our Ultra TR, we use input images, 384 plus 384. Actually, the image resolutions is not bigger than and is not good performance. Although you can try use the input resolutions are 124 plus 124. But I think it's not a good choice because it used a large GPU, and I think more labs or more schools don't have more GPUs. So
Okay, thank you. Is there any questions about the solutions?
Hello. I noticed that your method is similar to mine. May I ask if you added LoRa to all layers of the backbone?
you said the LoRa inject to where?
All layers.
Can you find the can you show the structure of your artist structures. I think he has some questions about some layers in your work. Yeah, that's right.
Oh,
Yeah, and the LoRa was injected into the QQA projection and the output projection and both MLP layers and not at another layer. It's the public injection.
okay, thank you.
Thank you. Is there any questions from other teams? If not, thank you again for your good solutions for challenges. Thank you again.
Yeah, thanks.
Next, we will investigate another team named label 105 user solutions. Hi, is there any members from this team? Lab 105.
Yeah, we are present. Is it? Can we start presenting?
Yeah.
Okay. I am having some trouble trying to find the present button right now.
I think you can from the above there is a button for share your screen. From that one.
Yeah, I'm trying to use the web version, so I'm not completely sure that I see anything.
Okay. Did you modify your slicers or not? I can.
Excuse me? Yeah.
I can share your slicers with my computers and.
Okay.
Okay. Do you modify that or not?
Yes, it's been slightly modified. I can mail it to you in like 2
Maybe
minutes.
this one is different from yours. I think you can
Yeah.
send email to me.
Yeah.
I will ask another team give the presentation.
Oh yeah.
The next
Yeah. Thank you.
next year. In this interview, you can send your slides with email to me. Okay.
Okay. Thank you so much.
Okay.
Yeah.
We will investigate another team. Major give the appreciations.
Hi.
Okay.
Can you see my screen?
Yeah.
Okay. Okay. We are Team Flamingo and from KTH, and this is our team member. And I'm Junjie Hu. I'm doing my master at Uppsala University. And for introduction, our dataset it include 40,000 around samples.
Sorry.
Sorry.
Can you show your whole slides because you do not open that in the screen.
Oh,
okay.
it go to another screen. Sorry.
Okay. Okay. Thank you.
Okay. Is it correct now?
Yeah, right.
Okay. So the data it includes 40,000 around test samples and include 4 task families: segmentation, detection, regression, and classification. And it cover 18 types of organ categorized like breast, fetal head, kind of, and 27 different specific tasks. And our motivation is the first is ultrasound image analysis inherently heterogeneous. As we know that different tasks require different outputs, such as mask, bounding box, and numerical measurement. And second is current practice is fragment. Most methods train separate model for each task, which leads to efficient training and poor knowledge sharing. So our purpose is to build a unified foundation models. And for the problem, we face several challenges: heterogeneous output space, optimization conflicts. We know that different tasks, they focus on different features. For example, the segmentation, it's focused on dense pixel features, while the regression and classification, it might focus on global features. And so our goal is to develop a transformer-based multitask ultrasound foundation models that achieve strong performance across tasks. And this is our paper. And first, about our methodology, I'm going to introduce our backbone, the encoder. Here we use a swing transformer, which has 4 stages, and these 4 stages multi-scale features will as input for the FPN decoders, and the decoder will concatenate these features together. And this is our global task regression head and classification head. For global tasks, we adopt lightweight prediction head operating encoder level features. Specifically, both classification head and regression head branches first apply global average pooling to obtain compact features representations. For classification, a simple linear classifier with dropouts is sufficient, as the task primarily requires a high-level semantic discrimination. In contrast, regression involves predicting continuous values and thus demand stronger modeling capacity. Therefore, we employ a multi-layer perceptron to capture nonlinear relationship between features and target variables. Additionally, scale normalization is applied to stabilize training and ensure consistent output range across different regression targets. Then is our dense task from the FPN decoder, the segmentation head, and detection head. We employ FPN-based decoder to preserve spatial information and integrate multi-scale features. For segmentation, the fuse feature map are first refined using lightweight convolution, group normalization, because we use a small batch size, and cell sigmoid linear unite. And this block appear twice. Then we use SMP segmentation head to get the mask. About the detection head, here we designed a sentinel type head. So first, we use a shared stem to extract some common features, followed by 3 task-specific branches, a heat map head for object-centered localization, a size head for bounding box dimensions, and an offset head for precise localization refinement. This design enabled efficient, accurate design, dense prediction while maintaining a unified architecture across. This is our experimental setup. So for the data set, we use 80 and 20, 80% for training data and 20% for validation. And we make sure that 27 subtasks are split equally to the training and validation set. And for pre-processing, we release the image size to 224 plus 224. And then we use image night normalization. And for augmentation, we use random brightness and contrast. Then we add the Gaussian noise. And for evaluation metrics, segmentation, we use dice, and classification, we use accuracy, and detection is IOU, and regression is MAE. For training strategy, for every batch, we only pick one single task. And after training, we will use weighted multitask loss. And this is our hyperparameter setting. The batch size we use 20 and epochs 50. And we compare that the small batch size is performed better than the bigger batch size. And the learning rate we use 1E minus 4, and the schedule we use constant and annual learning rate. And this is our G-flops. And G-flops vary by task due to task-specific heads. And our mean G-flops across 27 tasks is 22.1. And it ranges from 20.7 to 23.9. And the number of parameters and the training parameters is 93 million, and total the encoder it has 86, is quite big. And for FPN, it only had 2 million, also the head. And this is our results. Here we compare 3 different methods. The first is baseline, which is offered by the challenge. So here it uses the efficient net B4 from the team library, and the heads is quite simple. So it's only gets this result. And then we modify the backbone to the swing baseline, the swing base patch for Windows 7 2020 224, also from team library. It's get better, especially the segmentations. And our method, based on the swing baseline, we change each head. We use our heads introduced before, and it gets this result. And we also compare the different backbones, the ResNet, Vision Transformer, and the Swing Transformer. So we can see that our Swing Transformer gets the best, and the ResNet, it's the worst. And this is TSNE. This one is the baseline, and this one is our models. We can see that in this baseline, this area are mixed. And our model it's a bit separate, but also have some points mixed together. And this is our ranking. We get 8, but still have some problem with the detection and classification, maybe, and hard parameter sharing for swing transformer backbone is feasible for heterogeneous ultrasound task. And this is our code, and it's public. Thank you for listening. If you have question, please let me know.
Okay, thank you again.
Thank you.
Is there any questions about their solutions? I think he gave a deep analysis about some part like the classification task. Thank you. Is there any questions from other participants or other teams? If not, thank you again. We'll invite the other teams give the presentations.
Okay.
Okay. Hi. Any case? Yeah. From the team lab 105. I will say your share
Yes.
your slides now.
Oh yeah, please share. Okay, thank you so much. So, greetings everyone. I am Aniket Vajesh, part of Team Lab 105, and we'll be presenting our approach for the challenge. Could you please go to the next slide?
Okay.
So, as you know, the problem statement was the main issue with ultrasound imaging is that it's inherently noisy. It has varying acoustic windows. So the whole point of the challenge was to come up with a foundation model that can perform very well on 4 different tasks, given 4 different subtasks as 27 different subtasks as well. So yeah, please go to the next slide. So we have our this is a model architecture. So the shared encoder backbone, we used the ConvNXP to tiny encoder. And after that, for each of the tasks, we had 2 paths in which it could go. So for one of them, the yeah. So the 2 feature routings that could happen were one was for the dense prediction or the other for the global prediction path, and depending on which task was used. So the FPN decoders for the dense prediction and the global prediction path was the last feature map. And after that, the other novel aspect of our approach was that for each of the adapters, for each of the subtasks, for each of the 27 subtasks, we had squeeze excitation adapters. So the whole point of them being to mitigate a negative transfer and to just give at the end to the segmentation or detection or classification or regression head what was only absolutely necessary for them to make the final prediction. So yeah, that was the intent of the squeeze and excitation task adapters. And finally, for each of the heads, we have task-specific losses as well. The main aim of these are to counter the severe class imbalance and mitigate ultrasound noise and stabilize multitask convergence. For more, could you please go to the next slide?
Okay.
So the next slide is a more verbose explanation of our method, more or less. So we can skip this. And our share encoder was initialized with an FCMAE, which is fine-tuned on the ImageNet 20K and 1K weights. And then we used those as a good prior for extracting multi-scale hierarchy of feature maps. Now, please to the next slide. This is this is what our task adapter looks like. There is a residual connection from the input map down to the task adapter features, and we have an averaging and then global average pool. We apply the linear value, and then finally we have the sigmoid, which is then fed to the final layer. And the next slide is where we have the specific task adapters as well. And specifically in the detection head, we are using dense FCOS predictions, which is another novelty that we have. And then finally, in the next slide, we have the loss functions that we use for segmentation. It was pretty much the standard dice loss, nothing significant here. And then you have the for classification, we had a very specific version of the cross entropy that uses label smoothing. So that's what we mean by the soft target path. So instead of using hard as in 1 is equal to the correct class and 0 is for others, it uses 0.95 of the correct class distributes and 0.05% across the uncertainty. And the main aim is to just make it so that the model generalizes better and isn't overconfident even when it makes the final generalization. And yeah, the regression loss function is the normal average MSE loss. And finally, for the detection, we have binary cross entropy to determine if a pixel or anchor is truly the center of an object. And finally, we have the IOU loss attached to it as well. So instead of calculating the MSE on the 4 corners of the box, so the main point was it wouldn't account for the scale of the box. This calculates the intersection over union, and this penalizes the model in a much better and robust manner to get the detection and bounding box better. And you have the results here. Overall, we placed 7th among the 24 participating teams, and we have a normalized score of 0.8583. And the last 2 slides are just visualizations of the basic. The next 2 slides are essentially some visualizations on how our model performs and some of the predictions that it made. So yes. Last one, and the last one with the key point regression as well. That's basically our attempt at the challenge. Thank you so much. Happy to have been part of the entire challenge.
Okay, thank you for your presentations. Do you have any questions from other participants? If not, I have one question. Can you give some comments about this challenges? Which task do you think is most important? Why? Or the most challenging task do you think?
Hello, can you hear me?
Yeah.
I'm Anshuman. I'm also in the same team, Lab 105. Sorry, can you repeat your question? Which challenge is most important, or which task?
Which task is more difficult, do you think?
Oh, after a lot of experiments, we kind of realized detection was one of the most toughest tasks, for which we had to modify our detection head quite a lot. Comparatively, classification and segmentation were fairly very easy. I mean, model was able to perform quite well in initial trainings. We didn't have to modify it a lot, but for detection and regression tasks, we had to modify the loss functions and for the task head. I think those were difficult, but what is more important, I would say everything is important at the end.
Okay. Can you introduce your backbone, or you only use the simple architecture without any pre-trained models? Do you use
Sorry.
any pre-trained models in your architecture?
We used the backbone that we used was ConvexNet V2. Its weights were initialized using ImageNet, and we did not do any kind of pre-training after that. We directly used it for training the model for ultrasound case, but the weights were initialized using ImageNet.
How about your GPU used it in your experiments?
Sorry, I did not understand your question.
About your handwork for these experiments or training.
Oh yes, we had our own GPU clusters where we trained our architecture.
Okay. Thank you again. We
Okay,
will
thank you very much.
Thank next, we will invite another team from the first hospital of Lanzhou University. Give their solutions. Hi. 也在真的挺高，后面就是比较多，但是主题里的体系状。Next, we will invite another team, namely the first hospital of the Lanzhou University, give their solutions. Hi. Is there anyone from this team? Okay, if not, we will invite another team, namely the SCMU for this foundational model challenging our ultrasound image analysis.
Okay, can you see my desk?
Yes.
Oh, okay. Hello everyone, my name is Lin Hongshun. I'm present today is a unified mounting task learning forward for ultrasound image analysis. This competition has 27 small tasks. They are split into 4 tabs: segmentation, classification, detection, and regression. The tasks are about medical imaging, like scans of herbal bodies, injuries, and tumors. The training set has close to 300 images, and the invalidation set had more than 6,000 images. With so many tasks and different types of the images, it's hard to build a system that works for everything. So we want to build a system that can handle many different ultrasound tasks at the same time. We will use the model called MIT-B5. It's is the main part of this system. It will have multiple hands to deal with different tasks. We plan to train it into stack so that it can work well on the 26 different ultrasound tasks with higher accuracy. And the multi-task network we create use MIT-B5 as the common feature instructor, followed by four branches which handle different tasks. We use the one backbone to support all four types of ultrasound analysis and data, which allow which allows which allow that all tasks to be modeled together in the unified way. We use a Perchin hybrid transformer model called MIT-B5, which has original training on Imagine as our backbone network. It tracks extractor features in four stands. This site works well for the design pretty tasks like ultrasound imagery and analyze and can product robust and stable shell features that support many tasks. And our task special hand content of 20 segment tasks and 3 detailed tasks. Both of these tasks are based on the shared FPN. The segment hands use FPN and detection has used FPN and the fast RCNN. For regression and classify text, we use two kind of task hand. The three task regression. The three task regression had to output key point, and the 9 task classification had to output class probability. Ban, ban, both are based on the encode feature and go through global average pooling. And we use two-step training approach to balance both useful and task special performance. First, we train the model on multiple tasks together. It helps the share learn generate ultrasound features and build a set of granular shares way. Then for each of the 4 task types, we flatten the task heads and decode disparity. In the end, we gave 4 separately higher specially models. The first part of the per-training runs for 50 runs, and the learning rate for the encode and for the task hand is different. We choose the model that performs best on the evaluate date, which is split from the training date. The final safe model is named the MITB5 best model .pth. In the second stage, the start point is the way from the first stage. We train for 15 runs. Different parts like the path encoders, FPN, and task hence we use different running rate to get better result. We then save the best model for the 4 types of task. And perform the result of our model on all tasks is shown in the picture. In this ablation experiments, we use MITB5 as the baseline model and made several improvement. We first adjust the input size, which led to better segment performer. Then we add the first RCN detect model, which improve the detection result. Finally, we use two-stage training strategy, which further boost detection and regression. This result show that each model computers to multitask learning progress. And we built, and finally we can say we can see we have built a unified multi-task learning framework that works with many ultrasound tasks based on MITB5 used by efficient feature routing and standard training strategy. We balance the model performance, and the code will be open source. And thank you, everyone.
Thank you. You gave a very good presentations for consider for your first or second presentation. I don't know, but I think it's very good. This is a good beginning for everyone.
Okay, thank you. Thank you, teacher.
Okay. I have one question about your solutions. Your training your work with two-stage training stages. Did you compare the single stage stage ways and with the second stage ways?
This picture, can you answer your question?
No. I think you only use two-stage methods. Do you have some result about one-stage training results? Okay, I know. You just tell me the first from the first to third lines use one stage. Only the last one use two stage. Yeah.
I don't know.
我想问呢，就是说您的这张表格意思是说呢，就是说前三个结果呢，相当于都是用的一个阶段的，然后后边的那个最后一行是相当于两阶段的结果，是这意思吗？
对，yes.
Okay. Thank you. Is there any questions from other participants?
If you have any question, you can
You can task
in the this way.
Okay. Thank you again.
Thank you. You give me the 舞台 to practice my English. Thank you.
It's a good beginning for everyone like me.
Yeah. Very thank you, teacher.
Thank you again. Next we will evaluate that another team from Tianjin University.
Okay, can you hear me?
Yeah, good.
Okay, can you see my screen?
Yeah.
Okay, good afternoon, Professor Bry. It is my honor to present our research paper for the FMC UIA 2026 Challenge, ULUS, a unified multitask foundation framework for journalist ultrasound image analysis. This presentation will focus on the challenges, task requirements, and will be organized into 4 sections: motivation, method, experiment, and discussion. First of all, let's examine the motivation for this study. As a critical diagnostic tool in clinical practice, ultrasound imaging serves as a vital clinical diagnostic tool. Yet existing methods suffer from weak generalization capabilities and are often confined to specific tasks, making them ill-suited for analyzing multi-organ, multi-region ultrasound images. Especially, the challenge in ultrasound image analysis primarily lies in the difficulty of achieving price analysis of ultrasound images across multiple organs and lesions. Traditional task-specific approaches lack sufficient generalization capabilities, failing to fully leverage ultrasound data's information. Based on this, our research objective is clear: to develop a foundational universal model for ultrasound image analysis, enabling multitask processing, including classification, segmentation, detection, and regression, across multiple organs and lesions. This will advance the development and clinical applications of AI-driven ultrasound diagnostic. Next, I will provide a detailed overview of the methodological design of this study, which constitutes the core component of this research. Based on deep learning technology, we construct a unified, efficient, and highly generalizable foundational model for ultrasound multitask learning to address the current issue of model fragmentation. As illustrated in Figure 1, the framework consists of 3 core components: a modified shear backbone, a multi-scale feature pyramid neck, and decoupled prediction heads. To accommodate the diverse input dimensions of different ultrasound datasets, the input size is dynamically adjusted per datasets, ensuring optimal multi-scale feature extraction for heterogeneous tasks. Model training employs a multitask compensate loss function for joint optimization. The loss components for each task and their calculation method are as this. In terms of the backbone network design, we propose the C3 and VITB-V3 model as the core, as shown in Figure 2. This model features a dual-branch architecture. On the one hand, it extracts local features via 1x1 convolutions. On the other hand, it means global feature through stacked MVITB-V3 blocks. Finally, the features from the 2 branches are connected and fused to achieve complementary between local and global features. We have designed dedicated task headers tailored to different task requirements, and each task header has been adapted based on the multi-scale features of the backbone network. Detection header is a decoupling head that processes multi-scale features via classification and regression branches, achieving price localization through DFL-based bounding box decoding. This is calculation volume for the DFL model. Secondly, there is a classification head. Unlike the detection head, the classification head takes a single feature map as input. It uses a convolutional layer to map the feature channels to a 1280 dimensional space. After discarding spatial information via adapted average polling, it performs image level classification through a fully connected layer, thereby meeting the requirements for determining the overall category of ultrasound images. Thirdly, there is the segmentation head, which is also based on P3, P4, and P5 multi-scale features. It first uses convolutional layers to map features from different scales into a unified channel, then generates prototype features and mask coefficients by performing operations on these two components, such as this. It produces the final segmentation mask, thereby achieving pixel-level segmentation of the target region within the ultrasound image. First is drag-head, which, building upon branch detection, generates key point features by applying convolution to multi-scale features. It then performs numerical regression calculation on the ultrasound image via a key point decoder, thereby meeting the requirements of clinical measurement tasks such as femur length and cervical length. This is the formula for KPD model. Okay. After completing the model design, we conducted a systematic experimental validation. We will present the details of the experiments. We used a large-scale heterogeneous dataset comprising the 27 subtasks provided by the challenge to train the model comprehensively. The corresponding evaluation metric formulas are shown on the right. Next, we will examine the specific experimental results, which are divided into two parts, quantitative evaluation and visualization. First, regarding the quantitative evaluation results as shown in the overall score table, our model demonstrates solid baseline performance across all tasks, an average IOU of 0.7955 for the detection task, an average MRE of 40.63 for the regression task, and an average DSC of 0.7460 for the segmentation task, validating the model's effectiveness in multitask processing. Looks at the detailed scores for each task. In the detection task, the model achieved an normalized IOU of 0.9810, indicating excellent performance in terms of the normalized IOU ratio for nodule regions and very high localization accuracy. In the regression task, the model performed exceptionally well on the IUGC and FUGC datasets, with normalized MRA value close to 1, indicating minimal error. In classification task, header detection achieves excellent performance, and the sacral bone detection also performs at a high level. In the segmentation task, the DSC for fetal head segmentation reached 0.9772, indicating excellent segmentation performance. However, on the multi-class segmentation dataset for the head symphysis pubic region, the DSC dropped sharply to 0.4532, demonstrating a significant difference in performance. With conducted an in-depth analysis of the performance discrepancy observed in segmentation task and identified domain shift as the primary cause. Difference between the training and tested datasets, including variation in imaging equipment, operating physician, and fetal position, resulted in unstable generalization performance of the model on heterogeneous data. This represents the core issue that our future research must address. In addition to quantitative evaluation, we also conducted extensive visual validation covering both the validation and testing phase. Finally, we move on to the discussion section of this presentation. First, let us summarize the work of this study. First, we successfully constructed a unified multitask framework, ULUS, which effectively addresses the heterogeneity issue in ultrasound image. Second, by designing an enhanced ULUV11 backbone network, we significantly improved the modeling capabilities of both local and global features while maintaining lightweight and efficient performance. While summarizing our research findings, we also clearly recognize the shortcomings in our work. Based on this, we propose the following direction for future research and work plans. First, we will focus on enhancing the model's domain adaptation capabilities to address performance instability in classification and segmentation tasks across the heterogeneous data. Second, we will further optimize the model architecture to improve its versatility and robustness in complex clinical settings, creating a truly practical general-purpose foundational ultrasound AI model. That concludes our team's research on EULO-US. Thank you for listening.
Thank you, Dr. Liu. This is another solid and excellent presentation about their work. Different from the previous solutions, the TGU team use lightweight architectures to give a solution for these challenges. I have one question about your motivation of this choice.
Okay.
You use the YOLO solutions for this challenge, but this solution is lightweight solutions.
Yeah.
If in our challenging, we consider the inference time in this challenging, maybe you have a good score or good rank in this challenges. I want to know the motivation of your choice.
Oh, why we choose YOLO?
Yeah.
Since YOLO is a multitask model designed for practical implementation, our next why we choose mobile is our next step is to wrap the model using the Flex framework to provide the functionality in a more concise and user-friendly format.
Okay. I think this is a good directions because in our lab or in the future we want to apply this these technologies in some medical equipments. Maybe at that stage we should consider some lightweight solutions like the YOLO ones.
Oh,
Thank you.
Okay, thank you.
Is there any questions from other participants or teams?
Hello, I have one question. Yeah, I'm a little lost. So that your method is not based on the baseline, and so your home framework is based on the YOLO, and then you modify the different specific branches to achieve the classification, regression, and segmentation instead of only the detection, if I understand correctly. Or maybe you can go to the method picture.
Okay. This I choose the YOLO as the baseline and modified the backbone C3 and VTBV3 aims to lightweight our method. You can understand.
So you choose YOLO 11. Yeah, I remember you mentioned you use YOLO 11, and then as you mentioned, yeah, that's a lightweighted solution, right?
Yeah.
Okay, I understand. Thank you.
Okay, thank you. Is there any questions from other participants?
I have a question. Do you try the fast ASEAN compare the YOLO?
Oh, This is good question. Yes, our team hasn't conducted any other requirements, but we are currently adding ablation and comparison and other method to validate the importance of certain models.
So you use the fast ascent or no, or future use the fast ascent to practice?
I don't understand.
Uh,
Sorry.
I also sorry.
I think you can email with me.
Okay.
I
Okay,
think
thank you.
the fast ascent is another architecture, different architecture. Maybe that one is different with YOLO 11. Yeah.
Oh.
I think you can use fast ascent to detect some regions and also segment it. But I don't follow some recent works about that one. Do you is that new fast ascent can do four tasks? I don't know. Okay. Thank you again. If you have any question, you can email Dr. Liu and communicate with him directly. Thank you again.
Okay.
Thank you.
Okay. Next, we create another team, CZP 2025, give their solutions. Maybe this students he only want to predict his solutions in Chinese. Thank you. Give your solutions. Thank you.
I'm so sorry, everyone, but my English isn't very good. So please allow me to speak in Chinese. Thank you.
Okay.
我的这个题目是面向多任务超声图像分析基础模型的 Lawyer 方法。然后我的汇报可以分为以下几个部分。首先是要介绍挑战赛的任务背景和基线模型的问题，然后详细讲解我们提出的Lawyer 方法的3大创新，接着介绍一下实验设置和定量结果，包括相容实验，以及最后进行总结和展望。本次挑战赛聚焦于超声图像多任务分析，数据集包含27个子任务。但是超声图像在临床中广泛应用，不同设备、不同操作者以及不同解剖结构，可能导致图像的异质性很强，所以说需要一个能够统一处理多任务的通用基础模型。然后官方提供的基线模型是基于 FashionNet-based 编码器和多任务头。然后从我的运行结果来看，它在分类和分割任务上的表现是很好的，但在检测任务上存在了明显的短板。它的检测交并比只有 0.2980， 综合加权得分为 0.6713， 然后回归任务的平均绝对误差也还有很大的提升空间。所以说我们分析认为，检测性能差的主要原因可能有以下3点。第一是检测头过于简单，只有3层剪辑，难以捕捉小目标和稀疏样本。第二是损失函数只使用了 L1 损失和2值交叉伤损失，没有直接优化交并比这个核心指标。然后第三是多任务训练中，检测任务容易被分类和分割任务主导，产生负前移。此外，如果说直接对大型模型进行全参数微调，不仅可能会计算成本高，还容易在小规模的医疗数据上固拟合。因此，我们的目标是开发一个既能平衡多任务性能，又能显著提升检测精度的框架，同时能实现参数高效微调。然后针对以上问题，我们提出了 Lawyer 框架，它包含了3大创新。第一大创新是采用Lawyer 编码器，将Tiny 与 Lawyer 结合，实现了参数高效微调，解决了全参数微调成本高、易过拟合的问题。第二个创新是设计了优化的检测头。不好意思， 设计了优化的检测头和动态加权损失函数，直接优化交并比，这是检测性能突破的关键。第3大创新是采用了渐进式解冻策略，先冻结浅层，再逐步解冻深层，防止灾难性遗忘。这3大创新相辅相成，共同实现了多任务性能的全面提升。下面我将逐一介绍，然后整体的架构是如图所示。输入图像经过 Swim-Lawyer 编码器提取多尺度特征，然后被送入特征金字塔解码器，根据任务类型路由到不同的任务头。分割和回归使用全局池化头，分割和检测使用特征金字塔解码器特征。然后为什么选择 Swim Transformer？ 是因为它具有全局注意力机制，能够建模长距离依赖，而且层次化特征非常适合多尺度的任务。但直接微调大模型容易过拟合，所以说我们引入了 Lawyer。Lawyer 通过低值分解，将权重公斤表示为2个小矩阵的乘积，只训练新增的 Lawyer 参数，原始预训练权重保持不变，这样可以训练的参数会大大减少，降低了过拟合的风险。我们在Simultaneous 的 QKV 投影层都插入了 Lawyer 适配器，将质设为80，缩放因子为1。实验证明了这种方法能够保留 ImageNet 的预训练知识，又能高效适应超声图像。然后基线的检测头是3层卷积，通道数为128，难以处理小目标和稀疏的样本，所以说我们将其改进为4层卷积，中间通道增加到256，并进行了偏置初始化。坐标输出给一个小的正偏置，置信度输出给一个负偏置，这样初始训练时模型会倾向于低置信度，更稳定。同时我们设计了新的损失函数，在原有的坐标 smooth LE 损失和置信度损失基础上，增加了交并比损失项，即一减去预测框和真实框的交并比。我们给这3项分别赋予了权重，然后坐标损失是5.0，置信度损失为1.0，交并比损失为2.0，这样就能够优化定位精度，并且通过权重平衡梯度，避免了检测任务被其他任务压制。在训练过程中，浅层网络提取的是边缘、纹理等通用特征，深层网络提取的是语义等任务特定特征。如果一开始就同时微调所有层，就是可能会破坏通用特征，因此我们设计了渐进性的解冻策略。初始解冻 Swim 的前2个阶段只训练 Lawyer 参数和任务头，到第10个 ePage 解冻第3个阶段，第20个 ePage 解冻第4个阶段，这样参数先从通用特征开始学习，再逐步引入深层特征，训练就会更加稳定，避免了早期震荡。然后我们在官方数据集上进行了实验，按80%训练集、20%验证划分。Swim 系列输入的尺寸为224×224， CNN 系列为256×256，数据增强包含了随机亮度对比度、高斯噪声、水平翻转、平移缩放旋转。然后基础的学习率为1/4，Lawyer 参数学习率为减3，权重衰减为0.05，使用了5个 ePage 后皆余弦退回函数。评价指标方面，分割用了戴斯，然后分类用准确率和 F1 分数，检测用交并比。另外我们定义了一个综合加权得分，将检测、分割和分类指标按0.4、0.3、0.2加权，用于评估整体性能。然后表1展示了不同方法在验证集上的性能，可以看出IFFNet 的综合得分是0.6714，检测交并比为0.2980，而我们的 Swim-Lawyer 方法当质等于80，取得了检测交并比为0.7243的结果，相比了基线提升了143.1%，综合加权得分达到了0.8650，提升了8.9%。同时分割和分类指标也保持在不错的水平，这说明我们的方法在显著提升检测的同时，实现了多任务的平衡。然后表2是基于Simultaneous 的消融实验，纯 Simultaneous 的性能较差，检测交并比只有0.1987，但是加入了 Lawyer 后，分割和分类大幅提升，检测也有一定的提高，但是综合加权得分是在0.8112，单独使用了检测优化模块后，检测的交并比就直接跃升到了0.6794，但分类和分割略有下降，说明了检测优化模块对检测很有效。但需要结合 Lawyer 才能保持整体的平衡，将 Lawyer 和检测优化模块结合，在质等于40，综合加权得分为0.8625，当质等于80，达到了最优的结果是0.8650，这样验证了每个组件的必要性。 然后就是检测性能的突破，主要是得益于优化的检测头和动态的交并比损失。但我们也注意到，回归任务的 MAE 从基线的22.6增加到了61.2，说明检测大幅提升，对回归产生了负迁移，这是我们未来需要优化的问题。但是好消息是，我们的检测优化模块具有很大的通用性，在 ResNet 和 EfficientNet 上也验证过，都是有不错的效果的。从临床的角度来看，检测能力的提升对早期病灶定位至关重要。我们的模型向临床落地迈出了坚实的一步。当然，我们目前还存在一些很大的局限性，比如说回归性能有待提高，尚未在多中心外部数据集上进行验证，然后实时性也需要进一步优化。下面我来总结一下我们提出的 Simulawyer 多任务超声分析框架。通过 Simulawyer 编码器优化检测头以及动态加权损失和渐进性解冻，显著提升了检测性能，交并比得到了很大提升。综合加权得分也提高了28.9%，为超声基础模型提供了更强、更均衡的基线。未来工作主要是聚焦于优化回归任务、验证外部数据集以及模型轻量化和以及提升小目标检测的精度。然后最后感谢挑战赛的组织者提供的数据和平台，感谢实验室导师的帮助，谢谢大家。我的汇报到此结束。
Is there any question from other participants?
Can you speak Chinese?
看大家有什么问题？好，
就是我先问一下，就是你这一个的话，它那个 Swing Transformer 啊，你是有那个预训练的权重吗？
对，是有预训练权重的。
哦，那你是用的是什么版本的 Swing Transformer？
是 Tiny。
Tiny 啊，你有没有试过，比如说 Base 版或者 Large 版的？
没有，我目前只用了这一个版本。
然后你说用了 LoRa 方式训练的话，它效果比较好，如果直接全参数效果不好，是吧？
对，因为那样参数量有点过于大了，然后这个可以就是参数量能少一些。
过于大，为什么说参数量大反而不好？
因为全参数的话，它不就是那种，就是训练会比较复杂嘛。然后这样的话，就是微调的话，可能就是速度能快一点。
那你 LoRa 是怎么加的？就是相当于加 Transformer 每一层都加是吧？
就只在部分层加了，没有全都加。
那是加 QKV 那个 Self Attention 那一层，还是在 MLP 那一层啊？
是在 QKV 投影层都加入了。
投影层就是 MLP 层对吧？OK， 行，我这边没什么问题了，谢谢啊。
谢谢。
大家还有别的问题吗？没有的话，你翻到 PPT 的前一页，往下翻，应该是倒数第二页账号，不是，对，倒数那个就外部验证。实际上我们这个比赛是有外部验证的，就是说除了我们这个比赛之外，我们还有从非洲和那个西班牙那边拿的数据，然后呢，大家所有的方法也在那个上面去测了。当然，那个测的那个结果呢，没有纳入到这个比赛，就是说大家最后评分的这个部分。但是我们在那个，就是说那个就是总结论文的话会放进来。实际上大家还就是说整体所有的人在那个就是说外部的那个数据集上画画的效果还可以。我们有结果了，但是就是说还没有放出来，但是我们后边的时候写那个就是总结论文的时候会放进去，就是说外部验证。那么这样的话，我们就会有最起码跨3个州的数据吧。它因为有一部分数据是从非洲来的，有一部分是欧洲，然后我们的这部分的话是从亚洲这边，可能就会有一个跨州的一个部分。然后模型轻量化的话，可能我们是先把那个准确性提上去，然后再做那个轻量化。然后呢，实际上前边的应该是那个马岑博士，他们就做了很多的那个，就是说大模型做完了之后再微调，就是说增流啊，怎么回事，做那部分做的挺优秀的，他们队伍还有就是说他们课题组。然后好像就没有其他的了。 那你还有别的问题吗
我没有问题，老师。
？OK
那
OK
我就结束共享了。
OK. Thank you
好的，
again.
谢谢。
Next, we will indicate the missing group from the first hospital or London University give the solutions. Hi, Dr. Yan give the solutions about this. Okay. 嗨
稍等，我要退掉，重新启动一下这个腾讯会议。
，OK。
OK，就能看到我的屏幕吗？
Yes, yes, OK。
哎，那我还是拿中文讲吧，反正这个 slides 是英文的，就是拿中文我觉得能讲清楚一点。
可以，
然
好。
后这个，就是这个就是封面，然后我们是那个兰州大学第一医院的这个团队，然后呢，这个 challenge 呢就是，这个我就也不做太过多介绍吧，反正大家都是队员，然后这个就是做一个 foundation model，然后有4个主要的任务，然后呢，这个目标呢就是通过这个主办方给的一个数据，然后进行4个任务的训练，训练出一个模型能干4个任务，然后在主办方留的一个数据进行验证。这个我也就不说了。然后呢，这个是一个任务的总览图，呃，就可以，这个图上，呃，就可以看到有一些具体是哪些任务，然后，还有就是哪些部位啊，然后这个是我们的系统架构图，呃，我们的骨干网络还是用的一个Swing Transformer，然后我们用的是那个 Swing V2T，Swing V2 Tiny，然后输入的图像尺寸是384乘384，因为我们做过测试，这个呃比那个比那个224乘24整体会好一点，然后我们就最后采用了这个384乘384的分辨率，然后分辨率过去以后呢。这过去以后呢，我就详细的讲一下我们每个头，因为呃这个任务，我想大家在做的时候，如果有做的早的话，就是一开始主办方放了之前，主办方就是像白老师那边，白老师那边是放了2次数据，第一次放的是所有的数据，然后第二次放了一个 extra data set，然后那个 extra data set 里面包含了一个新的回归任务，然后呢，我们就发现一个问题。在这个回归任务，在这个新的回归任务放出来之前，用我们用这个 Swing Transformer 去直接进大杂烩的一个训练，然后分了4个头出来。这个时候好像对检测任务是影响不是很大，最后我们检测任务做到0.7左右，感觉好像没什么影响。当时我们想着随便提一提，也就上去了。但是那个 extra data set 一加进来以后，好像它其实对于整个来说，好像就加了几百个回归任务。但是我感觉大家应该就是之前如果一开始就在做的话，就可能会发现跟这个新加进来的数据集有关，也有可能跟这个新加进来回归任务的这个数量有关。但是呢，如果是后做的，这参赛队员就可能没有发现这个问题，因为后做的会一开始就把所有的数据下来了，然后他们就会发现一个问题，就是说如果把这个，我觉得大部分队伍都发现了一个问题，就是说，如果是一块直接扔到像 Swing Transformer 作为一个骨干网络的话，它可能这个就是这个检测的任务可能就会 crash 掉。后面我们就好好研究了一下这个问题， 我们就发现可能是应该可能是一些梯度的更新，然后被我们这个回归任务全部给抢掉了，或者说怎么样，就把这些检测任务这种相对精细的这种更新，就是权重啊啥的给破坏掉了。然后我们就想了一个什么办法呢？我们把检测任务就合并到分割任务里面去了。因为检测任务它提供的是两个坐标，一个是这个框的左上角，一个是这个框的右下角。然后呢，我们就把检测任务就变成一个分割任务，然后把这个框呢就变成一个 mask，就变成一个那种伪 mask，就可以看到我们这个这个是没有鼠标，就是这个图的最右侧的就是第三行就有两个图，就是一个白色的方框，就是我们的这个伪 mask，我们就是拿这个分割框的，就是这个检测框的这个框当做伪 mask，然后把它合并进了这个分割任务进行训练。然后呢，这样做的话，我们的检测分一下子就提上来了。而且呢，把分割任务好像也提了点儿。呃，但是这样的话，你推理的时候有可能它会推理出多个目标，但是我们观察一下这个数据集呢，好像这个检测任务只能检测出好像这检测任务是只有一个目标，所以我们就用 CV2 处理了一下，我们就把就是分割出的最大的一个框作为我们的结果，然后把它分割出来以后呢，再用 CV2 去呃将将这个分割出的结果，然后用一个更大的框把它框住，然后再计算它的左上角和右下角的坐标，然后作为我们这个呃检测任务的最终的结果。然后呢，我们检测任务其实这样做的话也是挺高的，最后可能结果是个0.79左右，其实也应该是检测任务也挺好的，能排前3左右。然后这是检测任务，然后分割任务呢，呃，就没有太大的那种创新的地方，因为我觉得分割任务这样做，其实效果也还可以，大家分割任务我感觉都是差不多的。然后就是我们就用一个就是可学习的这个 query，然后就去去收集这个收集这个叫什么收集一些信息吧，然后就呃作为，然后就拉了一个分割的任务头出来。然后我们的这个回归任务，可能是我们就是最好的一个任务，因为我们加了一个叫做这个 DSNT 的这个头儿和 DSNT 的损失函数。然后呢，有了这个头跟这个损失函数呢，它干了一个什么事情呢？它就是会把这个回归我们本来应该是正常做的话，应该是最大的就是可能性执行度最高的一个点儿，作为我们的最终的那个回归的坐标点儿。然后呢，这个 DSNT 它就干了个事情，它就是说它不是把执行度最高的作为回归点儿，然后它是那个区域，它把那个整个区域的重心作为回归的作为就是这最终回归的结果。然后呢，就是发现我们上了这个模块以后呢，这回归任务也是大幅提升。呃，就是虽然大家可能看就是我们在最后的这个就是不管是验证级和测试级，好像我们回归任务虽然是很高，但是也没到第一。但是就是白老师刚才说的，其实是有一个外部测试级的。我们在那个外部测试级上的回归任务，不仅是第一，而且是那种就是断了一档的那种第一。就可能比其他的队伍那个 M2E 就是小了一个数量级，甚至有些小了2个数量级。然后这是我们的回归任务。最后一个是这个叫什么？分类任务。分类任务呢，我们是先之前是我们做分类一直不太行，然后我们把分类就做了一个分割先验，然后就是先把它分割，就是先把这个需要分类的图用我们现在已经训练出的这个呃模型呢，去先跑一下它的分割任务，然后把它的分割任务分割出的东西跟它分类任务的那一整张图，下来等于就是2张图，一张图是它的原图，一张图是它分割出来的这一部分。 然后这两部分呢，去做一个就是展平，然后再用一个 query 去收集它的一些信息，然后最后能进行一个分类的结果的输出。啊，这个就是刚才我已经讲到了一些东西，这可能就我看是有说英语的队伍在，所以我这个 PPT 我就多停留一会儿，呃，就是分割和检测就是并到一块儿去了，然后分类部分就是用了一个分割先验，然后回归部分用的是这个 DSNT 的这个头，然后这个是我们的 loss function，就是一些很基础的，在我们在 loss function 上没有做太大的这个 innovation。然后这个是一些就是细节，就比如说我们的输入是384，然后我们的用的就是这个数据增强，就是一些color jitter，然后还有一些随机的 resize，呃，然后我们的训练的 environment 是一个就是英伟达的 L40，然后用的是那个 Adam 的那个 optimizer。然后这个是我们在这个验证集的结果，我们的 DICE 呢是0.89，然后这个 IOU 是0.78，最后测试集可能还应该更高了一点。然后这个是就是我们在验证集的这个分类，其实这个结果是挺不错的，就是用了我们这个分割先验，然后我们以为呃测试集也会还可以，但是我们测试集好像就不太行，这个目前我也没找到原因。然后我们的回归任务是做到了18.8，这是在验证集，然后测试集应该也是差不多，也就是18、19左右。还有白老师刚才说到一个外部测试集，那个我们的泛化能力是远远的要高于其他队伍的。这个是我们最后的一个结果。我就讲这么多。
Okay. Do we have any questions? 大家有什么问题可以问一下那个杨老师，他在这个方面做的很专业。
是的，我发现确实你很多数据都分析的很到位，比我们做的分析很到位。就我问几个问题哦，第一个就是你刚刚说的那个重心点是什么方式去做的啊？
它这个就是你可以看这个右上角它有个叫 DSNT regression 的这个东西，然后呢，嗯。它其实就是数学上的一个算法，然后它会把一些，就它会把这个整个区域全部纳入进去，全部纳入进去，然后只会挑这个区域的，它不是说挑这个区域的，就是概率最高的一个点，而是会把整个区域都考虑进去，然后把它的重心拿出来当做最后的回归点。其实就是如果是你去 Google 一下的话，就是不搜别的，搜这个 DSNT 的，它是有一篇论文的，然后我们就是参考那篇论文。
叫做 DSNT 对吧？
对对对。
行，我觉得你做的东西还是比较深入的。对，然后你说那个什么分类哦，分类你不是用了那个分割的结果输入到分类嘛，对吧？
对对对。
其实另外一个 challenge 就是另外一个也是那个杨鑫学长
就
杨老师，
CSV 的那个是吧？
对 CSV 我也是用这种方法就提点了。
提的是我是也提了，但是我们那个 CSV 就是那个竞争太激烈了，
是的 CSV 太卷了，我刚开始都进前10了，后来越来越后，反正我用这个你说的这个方法是提升了，就是把那个分割结果放进去。
对，这个是能提升一点的。
老师可以加个微信吗？下来我们可以聊一下。
我这微信在最后。
行，我截图一下。好的，行，我这边没什么问题了，谢谢白老师啊，没什么问题。还有杨老师，谢谢。
OK。 大家还有别的问题吗？从其他队伍的？OK，如果没有的话，我们就下一组，好吧？好，谢
我
谢
接个步
杨老师。然后我们等一下的时候找下一个队伍。Next we will investigate another team, named the deeper gives solutions. Hello, is there any members from the deeper team? The title is a double encoded based on Next multitask learning framework for ultrasound image analysis. If not, we will evacuate a good team from named the VCBC give their solutions. Their solutions have good performance on two tasks. Okay, thank you.
Good afternoon, everyone. I'm Yugo Tan from the big team at the University of Electronic Science and Technology of China. Let's start with the big picture. Ultrasound is a lifesaver in clinical diagnosis. Ultrasound is safe, real-time, and used everywhere now. But here is the problem. Analyzing these images across different organs and diseases is incredibly tough. So, how did we think of the challenge and our solution? Here is the problem. Traditional methods are too narrow. They are built in for one task and failed on other tasks. On the outside, new foundation models based on large language models are powerful, but they are hungry because they need massive computing power and months of training. And that's just not practical for most hospitals. Our goal is to get a balance between them. We aim to build a generalized efficient system using tools like NUNet and Europe. Now I want to give a common misconception. Many people think Euro is just an object detector, but it's already a vision foundation model. Euro can handle detection, segmentation, key-point regression, and classification tasks. It's the whole idea behind the foundation models. Sure, it cannot solve NLP tasks yet, but for this challenge, this is a totally visual task. For data preprocessing, we build a strict preprocessing pipeline to keep everything consistent. First, we reset every image into a square of 256 using bilinear interpolation. And for the label of each task, we mathematically shrink the bounding boxes and key points exactly the same way. And detection coordinates became relative values between 0 and 1. Regression targets were scaled using min-max normalization. And our strategy was very simple: to divide and conquer. For segmentation task, we stuck with the gold standard NUNet, and it just works. For classification and the detection regression task, we all use the YOLO model. And for compression, we use the Convex and the Dino models as a backbone to extract features from the images. And they are fed into a machine learning model such as random forest to make predictions. And let's look at the numbers, the results for the classification. We combined our fine-tuned YOLO model against these backbones with machine learning classifiers. And this is the results. You can see that YOLO model had its own, and in some cases, the final YOLO model beat the former methods on these metrics such as accuracy, kappa, and F1 score, especially on rare classes. It proves that for specific medical tasks, a well-chosen lightweight model can outperform massive backbones like this. And this is the classification task. And for regression and detection task, the table shows the results. In regression, the YOLO model achieved the higher R-square and lower MAE than the compared backbones. And in detection task, the YOLO model outstanding. YOLO fit this data perfectly, making it more accurate than pure CNN or variant transform backbones. It's our conclusions. And we also run some ablation study to fine-tune our setup. For example, for NUNet, we test 3 epochs, 500 epochs, and 1000 epochs. You can find that with more cost, the performance is not very. The improvement is very little. Perhaps 300 epochs is enough if you can consider both the training cost and its performance. And for other tasks, we test two versions of YOLO, the version 8 and version 11. We use the medium weight. We test the other hardware parameters to get the best and for the external validation set, here is the results. We ranked nothing this set. We ranked extremely high in detection and regression tasks. This leads to our main conclusion. YOLO isn't inferior to foundation models used in other teams. In fact, for these clinical tasks, a specialized efficient YOLO pipeline can match or even beat massive models, but with a fraction of the cost and the training time. That's all our presentation. Thank you.
Thanks, Dr. Tan. He's an expert in computer vision. I think he participated the past 2 or 3 challenges we organized.
Yes.
Do you have any questions from other participants?
Hello. Yeah, I have one question. Can you go to the method part?
The method.
Yeah. It seems from what I understand, are you using the different model together to get the output, the result?
Yes.
Not if I understand correctly, right?
Yes, it's not a unified model.
Oh, okay. So, yeah, that's my question. Yeah. Thank you.
Yes, it's a good question. In other teams, in their slides, they said that when they train their model, like example, if the performance of detection behaves higher and the regression, the performance of the regression may be lower than before. That's a trade-off between different tasks. And I also tried a different way my work is to train different models in each subtask, and the performance on detection and regression is very high. Because of the performance in segmentation is a little lower than other teams. That's really what we need to think again. Okay, thank you.
Yeah, because if I understand correctly, yeah, as challenge is like want to us use a unified model for the all task. Yeah, but you mentioned the Euro is like for 3 tasks. Yeah, I think it's kind of like the unified segmentation. Yeah, unified foundation model. Thank you. Yeah, thank you for your presentation.
To be unified or not is a question. We are trying to solve these questions in the future.
Okay.
Yeah, thank you.
Okay. Any questions? Okay. Thank you. Thank you again, Dr. Tang. I think in the future we want to invite you to organize a team for another challenge in McCann 2026. The challenge is about foundational models for biometrics in ultra image analysis. We can talk this later. I think in that task, your master can get a better or best performance in all challenges. Thank you again. Next, we will invite the last team from Wuhan University's give their solutions. Okay.
Okay, can you see my screen?
Yes. Yeah.
Okay. Hello, everyone. It is a great honor to share our work titled A Unified Framework for Ultrasound Image Analysis based on category-wise hard parameter sharing. I'm Xu Wenqiu, representing Team Sigma from the School of Computer Science at Wuhan University. And our presentation consists of 5 parts: research background, methodology, experimental setup, results, and finally conclusions. Let's begin with the research background. While ultrasound is a critical diagnostic modality, automated analysis remains challenging due to inherent speckle noise, varying imaging protocols, and operator dependence. Traditional approaches typically develop isolated models for specific tasks, which lacks scalabilities. To address this, the Foundation Model Challenge for Ultrasound Image Analysis 2026 introduced 27 diverse subtasks across 4 diagnostic categories. And our objective was to construct a single unified framework capable of generalizing across this extensive multitask distribution. To achieve this, we designed a framework with 3 core highlights. First, we use a powerful pre-trained vision transformer, DinoV2, as our universal feature extractor. Second, we introduce category-wise hard parameter sharing. Instead of forcing all 27 tasks to share one weight, which causes negative transfer. We let tasks within the same category share weights, while keeping the four main categories independent. Finally, we use knowledge distillation and semi-supervised learning to give our model an extra boost on complex tasks. And here is the overall architecture. The framework is built upon the DNOV2 backbone. To mitigate the previously mentioned negative transfer, we trained 4 sets of weights for the DNOV2 encoder, one dedicated to each category. Within the specific category, such as segmentation, or subtasks jointly train and update that single encoder. This allows us to share knowledge where it helps and separate it where it hurts. And to generate the final predictions, we attach lightweight task-specific heads to our features. A crucial detail of our architecture is that all 4 prediction heads exclusively use the final feature map from the DNOV2 encoder, specifically from block 11. For segmentation, we use a simple 1-by-1 convolution followed by 16 times upsampling to recover the original resolution. For classification, we compress the features using global average pooling before passing them to a linear classifier. For detection, we artificially construct a simple feature pyramid generating 4 scales from that single last layer feature map, which then fits into a decoupled head with 2 branches, a regression branch for bounding box coordinates and an objectness branch for target confidence. And for regression, we use a heat map-based approach. A unit-like decoder progressively upsamples the feature to generate an auxiliary segmentation map and a per key point heat map. We then apply a differentiable soft argmax operation to convert these heat maps into precise continuous coordinates. And to help our student model, we brought in expert teachers and utilized the unlabeled validation data. The alignment mechanism here is key. For detection, we use a fine-tuned YOLOv8 model. The YOLOv8 teacher provides a bounding box, and our student model then calculates the loss specifically at the grid location corresponding to the teacher's box center. For regression, we use a pre-trained transunit. The transunit teacher provides a pseudo-segmentation mask, and the student's auxiliary segmentation branch is forced to mimic this mask. By learning the anatomical structures first, the model's heat map localization becomes significantly more stable and accurate. And our objective functions are carefully matched to these architectural designs. Segmentation uses multitask dice loss, and classification uses cross-entropy. For detection, the total loss is a combination of bounding box regression loss, classification loss, and the teacher's distillation loss. Finally, or similarly, for regression, our total loss combines the smooth L1 loss for the final coordinates prediction with the cross-entropy distillation loss from the auxiliary segmentation branch. This ensures the network learns both the precise points and the overall structural context. We then trained our models on the challenge dataset, resizing all images to 448 by 448 pixels. We evaluated our models using task-specific matrix, DICE score for segmentation, accuracy, and AUC for classification, IOU for detection, and mean radial error for regression. During training, we used a uniform sampler to ensure the model saw a balanced samplings of subtasks from within this category. And here are our quantitative results evaluated on the validation set. Our method performed exceptionally well on dense prediction tasks, with the mean dice for segmentation reaching 0.9027. The classification AUC reached 0.9228, and the regression task also showed strong performance, with the mean landmark E reduced to 16.7697. However, the performance in detection was not as competitive. These numbers indicate that while the DNOV2 backbone combined with category-wise sharing extracts highly relevant spatial features, It likely struggles with the multi-scale localization required for complex detection tasks. So what did we learn? Our success in segmentation and regression shows that hard sharing efficiently boosts positive transfer when the tasks require similar structural understanding. The trans-unit teacher and semi-supervised distillation were clearly the right choices for regression, but for detection, the simplified feature pyramid had likely lacked the multi-scale robustness needed to find tiny anomalies. Moving forward, we need better data processing for class imbalance and a much stronger detection mechanism. In conclusion, we proposed a unified category-wise sharing framework using DNOV2 for ultrasound analysis. We successfully proved its strengths in segmentation and precise biometric regression. While classification and detection remain challenging, this sets a clear path for our future work. We plan to explore parameter-efficient fine-tuning methods like LoRa to improve efficiency and develop a cross-category soft sharing mechanisms to bridge the gap between tasks. Finally, let me briefly introduce our team. We are Team Sigma from Wuhan University, led by Professor Bo Du and Associate Professor Liu Yangtong, and these are our team members. Thank you for your time and attention. I would be happy to answer any question you might have.
Thank you, Dr. Chu. Do you have any questions from other participants? Master Chu, yeah. If not, I have one question. Do you compare the Novo 2 with Novo 3? Because there a new version of this self-learning foundational models. You use the old one, yeah?
Well, you mean the backbone?
Yeah.
Or yeah, we compared many foundation model and by experiment we found that DNOV2 performs well.
Can you give some comments about this findings? Or this observed phenomena?
Yes, the results we didn't picture it on the PPT, but we compared DNOV2 and DNOV3. Yeah.
Okay. In our previous papers, courses with your teams, the reviews ask us to do some experiments compared version 2 and version 3. We found the performance became better in the in one segment in the previous challenge your team participated in. So I'm worried about this one. Maybe we should investigate further. Thank you again. Okay. Last, I will give a conclusion about this this challenge. Okay. Thank you everyone for your contributing. We look forward to meeting with you in London. There are 16 13 participants. We will upload the printed videos in some platform. I think everyone and other people can learn it from your solutions. Next, we will some coming events in Macan 2026. We have one workshop about the medical world model and 3 challenges. One is about ultrasound. Its title is Foundation Model Challenging for Ultrasound Biometric. Another 2 is a metro or automated analysis using multi-mode imaging data. Another one is universe melt squeeze, melt synthesis, and melt wheel CIMR segmentation and qualification challenge. Associated with this event, we have another special issues on IE-TBME associated with the medical world model. We want all the participated attended our events. If you have good or excellent works, you can submit it to our workshop. You also can extend your work, then submit it to our special issues on IE-TBME. Another one, we also have another collections about the data set, but this data set is about the signal. That is another pictures about call for papers. If you have one, you also can contact me or submit your works directly in scientific data. Thank you, everyone. Here is my WeChat account. You can add me, and if you want to know more about this challenge, I can tell you directly. Finally, this part is about group discussions. Do you have any questions about this challenge? You can ask me questions with Chinese or English directly.